In this video, we're going to work through one example of a linear programming problem. Along the way, we're going to hit some smaller skills like solving systems of equations and graphing linear inequalities, but the main focus is going to be solving this word problem. You'll want a calculator and your sheet to take notes along with this problem, so grab those out and we'll get started. With linear programming, usually the idea is to maximize something within a set of given constraints. So what I mean by that is there's a lot of times in life where we're trying to maximize something. So like resources in life are limited, so we want to spend the least amount of our resources, but maximize what we can within those constraints. Which is getting a little philosophical, but this is just a mathematical way of doing that. So let's see what this problem says. It says Lenny creates concrete lawn ornaments and sells them at craft fairs. He has a large inventory of two of his favorite pieces, a soaring eagle and a white-tailed deer. However, they are quite heavy as the eagle weighs 45 pounds and the deer weighs 75 pounds, right? Because they're made of concrete. So he cannot take all the pieces because his trailer is only rated for up to 2,250 pounds. And additionally, the craft fair only allows him to bring 36 pieces due to limited booth space. So you can already see what we're trying to do here. So he's going to be selling these things at craft fairs, so he wants to maximize his profit, but there's certain constraints, like his trailer can only hold 2,250 pounds, and the craft fair only lets him bring 36 pieces. So imagine if you're Lenny and you're packing up everything to go to this craft fair, the question would be, how many of each would you want to bring? So here's the essential question, and it gives us a little bit more information. It says Lenny makes a profit of $80 on each soaring eagle and $120 on each white-tailed deer. Assuming he will be able to sell every piece he takes to the craft fair, how many of each piece should he take to maximize his profit? And then what is the maximum profit he can make? So like I said, we need to figure out how many of each piece should he be packing up. And at first, when you see that you can make an $80 profit on soaring eagles and $120 on deer, you would think, oh, just bring as many white-tailed deer as you can because you make the most amount of profit on those. And if we're assuming that we're going to sell everything, yeah, just bring the most amount of deer. But then if you look back up here, it says that the soaring eagle weighs 45 pounds and the white-tailed deer weighs 75 pounds. And remember, your trailer has a 2,250 pound limit. So yeah, you make more money with the deer, but they also weigh more, so you can't bring as many along with you. All right, so let's work through this problem and see how we can solve this mathematically. The first vocab word we see here is objective function, and that's just the thing that we're trying to maximize. In this case, it's profit. So let's write out an equation for how we make profit. And in this case, he makes $80 for every soaring eagle, so we'll say $80 times, and then I'm not sure how many eagles, so we're going to have to use some variable for that. I'm just going to leave a blank for now. Maybe for now we can just write the word eagle in there. So $80 per eagle, and then plus he also makes $120 profit for every deer. So we'll say 120 times, again, we're not sure how many deer he'll bring, so we'll just leave this kind of blank for now. And so the main question is how many of each of these should he bring? So the first thing we need to do is define our variables. There's two things that we don't know, and so I'm just going to call them x and y. For x, we'll say that's the number of eagles, and for y, we'll say that's the number of deer. So we're starting to mathematically model this setup, and the first thing we're doing is we're taking the unknowns from the problem and we're turning them into variables that we can solve for. So let's come up with these inequalities so that we can solve this system. It says write the inequalities for the two constraints. I guess constraints is like the next vocab word here. And if you've never heard constraints, it really just means restrictions. So thinking about this problem, we need to figure out how are we being restricted? Well, one way we're being restricted is the trailer can only hold 2,250 pounds. So we have a weight restriction, and then we also have this that says we can only bring 36 pieces due to the limited booth space. So I guess you could say space or just number of items, and we can come up with inequalities for both of those. As far as the weight, we know that, let's see, an eagle weighs 45 pounds, so we'll say 45 times, and now we're saying the number of eagles is x. So now I can say 45 times x plus, and then 75 pounds for each deer, so 75 times y. And if you add up this total amount of weight, that has to be less than or equal to 2,250 pounds, right? Because it can't be more than that. It's okay if it's less than, it's okay if it's equal to, but it can't be more. And then as far as space, we can only bring 36 total items, right? So it would have to be less than or equal to 36. And the number of eagles is just x, number of deer is just y. So we'll just say x plus y. Now these are both linear inequalities, and we can graph these. And you got to remember back to Algebra 1, but when you graph two linear inequalities, the solutions are in the double shaded region. which is just another way of saying that there's going to be a lot of points x, y, That would work for both of these inequalities, but we want to find that maximum point. All right, so let's graph both of these inequalities. Right now they're both in standard form, so if you've never graphed lines in standard form before, I just want to show you how you can do that quick. The main strategy is just to come up with x and y intercepts, because if you know where it crosses the y-axis and where it crosses the x-axis, you could just connect those points really easily, making a line through them. So if you look at this inequality first, we've got x plus y is less than or equal to 36. I'm actually going to think of this for now as x plus y equals 36 and just graph that line first. So if I want to come up with the y-intercept, I'm looking at some point on the y-axis, and I'm not sure where it's going to be. In other words, I don't know the y value, but I know the x value for the y-intercept is going to be 0. So if I plug in 0 into this equation, I'd have 0 plus y equals 36. And so then the solution, y equals 36. All right, so I know the y-intercept is 0, 36. And if I plugged in 0 for the y value, it'd be the same thing, right? We'd get x equals 36. So the x-intercept would be 36, 0. And I'll do the same thing for the other inequality. First, we'll think of it as 45x plus 75y equals 2,250. But then that's kind of an annoyingly big equation, and I feel like I can simplify it. And actually 45, 75, and 2,250 are all divisible by 15. So if you do that, you can just type that in your calculator quick, but 45 divided by 15 is 3. So we've got 3x plus, and then 75 divided by 15 is 5, so 5y equals, and then 2,250 divided by 15 is 150. And because we did the same thing to both sides, we divided everything by 15, these equations are basically the same thing, or at least they can be represented by the same line, okay? So I'm actually going to graph this line, which, I mean, they're both the same line, but this is easier to think about because the numbers are smaller. But I'm going to do the same thing as before. If I plug in 0 for the x value, I'd have like 3 times 0 plus 5y equals 150. So 3 times 0 just goes away. And if I divide both sides by 5, y would equal 30. Okay, so this has a y-intercept of 0, 30. So now I'll leave the x alone and plug in 0 for y equals 150. So this goes away. And now if I divide both sides by 3, x would equal 50. All right, so we have an x-intercept of 50, 0. All right, so I guess it's about time that we start labeling the axes so we can put these points on the graph. So I'll start here with the 36s. So you get a line like that, and we'll try and color code these here a little bit. And then for the other line, we've got to plot 0, 30, and 50, 0. So 0, 30 is here, and then 50, 0 is way out here. And then we get a line like that. Now remember, we started with inequalities, and what I graphed, the lines here, those are just equations. So with inequalities, we have to shade these. Now the formal way that you check this, like probably the way you learned in Algebra 1, is you find some test point on the graph, you plug it into the inequality, and then you see if it's true or not. Right, so for instance, I could pick 0, 0 as my test point, and if I plugged that into this equation, if I plugged 0 in for x and 0 in for y, is that less than 36? Yes, it is, right? So 0, 0 is true. That means it is a solution. Okay, so I'm going to use this color and shade underneath that line. I'm going to shade on the side of this line that has the 0, 0, right? So underneath it. And we could do the same thing for this other one. We could plug in 0, 0, which would make all that just cancel out, and of course that's less than 2,250. So 0, 0 is just the nicest point to pick just because it's really easy to plug in. But you can't do that if the line is going through 0, 0. Okay, but it worked for this one because neither of these lines were. So we're going to have to shade underneath that line. So now you can see the area on the graph where we have both colors shaded in. And it's bounded by these points, which we call critical points. So the entire double shaded region, we call that the feasible region. And the critical points are just the corners of whatever the shape ends up being. So mathematically, any of these points in the feasible region are solutions, meaning they'd work in the setup for this problem. Like 10, 10, right? Could I bring 10 of each? That means I'd have 20 total lawn ornaments, right? So that's under 36. And if I plug 10 in for both of these up here, that would still be under the 2,250, right? Because it'd be like 450 plus 750, which is 1,200, so we're good there as well. But we don't want any old solution, we want the one that maximizes the profit. So first let's list out what these critical points are. Right, this one, that was our y-intercept of 0, 30. This one was the x-intercept, 36, 0. And I'm not going to write this one because obviously we don't want to bring 0 of either. That doesn't make any sense. But now this one is a little bit tougher to figure out. My graph might not be perfectly accurate, so I'm not going to get that point just by looking at the graph. I'm going to solve this as a system of equations, and that will tell me where these two lines meet. except actually I'm going to use the simpler version of the equation. So here's the system we have to solve. And it's set up pretty well for me to do elimination right now. So I'm actually going to take this second equation and multiply it by -5. So that would give me -5x minus 5y equals -180. And now I'm going to add these two equations together to eliminate the y's, right? Because we've got positive 5y and negative 5y. We've got 3x minus 5x, that would give me -2x, and 150 and -180, that would give me -30. All right, so dividing both sides by -2 gives me x equals 15. So there's our solution for x. And now if I plug that back in, I'm going to use this equation because it's the simplest. Right? So we'd have 15 plus y equals 36. Subtract 15 from both sides, and you get y equals 21. So that solution, that's the point where those two lines meet. Right? So that's our other critical point. It would be 15, 21. So now that we have our critical points, our next step is going to be to test those in that objective function from the beginning to see which combination gives us the biggest profit. So remember, our profit equation was 80x plus 120y. And here's our three critical points. We're just going to plug each of these in. So if I plug in 0, 30, that'd be 80 times 0 plus 120 times 30. And if you type that into your calculator, you get 3,600. The next one would look like 80 times 36 plus 120 times 0, so this just cancels out. And 80 times 36 is 2,880. For the last one, we've got 80 times 15 plus 120 times 21. And if you type that in your calculator, you get 3,720. So of these three numbers, the biggest is obviously 3,720. That's the maximum profit we can make. So we answered that question. And when it says how many of each piece should he take, well, we said X was the number of eagles and Y was the number of deer, so he should take 15 eagles and 21 deer. So remember in the beginning, we said we thought he should probably bring more deer because those made him the most profit compared to the eagles. But since they weighed more, we knew we weren't going to be able to take just all deer. So by using this linear programming, we figured out specifically how many of each should he bring to maximize that profit. So that's it for this linear programming problem.